Could you see my slide, Pak Zul?
Yes.
Okay,
Yes.
thank you very much. Good morning, good evening for everybody. Thank you for joining the international virtual courses on volcano monitoring at ITB in this morning. Let me introduce myself. My name's Andri Dian Nugraha. I am from Global Geophysical Research Group, Geophysical Engineering, Faculty of Mining and Petroleum Engineering, Institute Technology Bandung. So today I would like to talk about the introduction to volcano seismology. So this is the outline of my talk in this morning. The first is introduction of the volcano seismology, and the second is a brief review of volcanic seismology, and the third is origin of volcanic tectonic earthquake, and the fourth is types of volcanic tectonic earthquake, and the last part is the information of deployment of temporary seismograph in Agung Volcano Bali in Indonesia. Actually, Pak Professor Sri Widiantoro already mentioned in the beginning of the talk. Okay, this is the introduction. Actually, volcanic seismology is science about signals originating from the volcanoes and associated with the volcanic activity. So the volcanic seismology, including first the origin of the signals, and second about the spatial temporal distribution, and then their relationship with the volcanic processes, and then using them as an instrument to investigate the volcano deep structure and also to predict volcanic eruption. So actually the subject of volcano seismology lies in the interaction between volcano and seismotectonic processes. And this is the volcanic term actually. So volcano is a fan or chimney which connect a reservoir of molten matter known as magma. So I think everybody already hear about a magma in depth of the crust of the earth with the surface of the earth. And the material ejected through the fan frequently accumulate around the opening and building up a volcanic edifice. And the material ejected actually consists of liquid lava and broken fragments of a partially or completely solidified rock as pyroclastic debris, and as well as great quantities of gases. The gases are the main force or the most important factor in the volcanic action actually. So this is the main elements of the volcanic edifice, as we can see here in the figure here. So actually, the volcano cone is a result of the accumulation of ejected material around the fan, and also the crater that is surface connection of the volcanic conduit through which the ejected material reach the surface. It may be located on the summit, something like this, or summit crater, and or within the plain cone here, located on a slope of the central volcanic cone, or we call the plain crater. And the caldera is an enormous crater, actually representing a large depression in the truncated summit of a volcano. So beneath a volcano, a magma feeding system of the volcano consists of the deep magma reservoir or chamber, yeah, something like this. We can see here that is reservoir of the magma in the shallow part of a lithosphere from the which volcanic material is derived. And the intermediate magma storage in location here, a place between the magma chamber and the earth surface where the magma may be collected before an eruption. And the feeding conduit is the connecting the magma collector with the surface. This is the feeding conduit actually. And the lava is the product actually, the surface appearance of the magma collectors with the surface. And about the volcanic eruption, so volcanic eruption is a process of material transport from the earth depth or earth interior to the surface. And surface manifestation of the volcanic features during the activity of basaltic volcanoes that we can see here. This is the example. Actually, we extracted from Jobin 2012. This is, we can see here the fissure eruption in 1975 of the new Tolbachik volcanoes in Kamchatka. So actually, we can see here, this is the eruption from the new cone and its lava flow. Yeah. Another example, lava fountain and spatter cone on Kilauea volcano, Hawaii. And this is the other example. This is the lava flow on Etna volcano, occur on in November 1989. So another surface manifestation of volcanic features during the activity of andesitic volcanoes. We can see here, this is the picture from Izbekov in 2012. We can see here the picture. This is the block lava flow moving down the flank. So this is from the Bezimiani volcano, Kamchatka. And this is another example, lava fountain and spatter cone on Kilauea volcano, Hawaii. And this is from the explosion at Kiziman volcano, Kamchatka. So another surface manifestation is dacitic volcanoes. Yeah, we can see here. This is the picture from lateral lava dome, Showa Shinjan, Usu volcano, Hokkaido in Japan. And this is a picture from surface deformation caused by the explosive activity at Karimsky. So similar to the earthquake, actually in earthquake it's generally well known about the energy of the earthquake, something like magnitude. So similar to volcano, we also use the volcano VI. Yeah, actually the volcano
Sorry, I think something wrong with internet connection.
Sorry, I have trouble in connection. Pajul?
Yeah.
Could you hear me? Sorry. I will be back. Okay. Could you see my slide?
Yes.
So from this one. So I lost my connection.
Yes, yes.
Okay, okay, okay. I think this is the last one. Okay, this is the surface manifestation of the volcanic feature during the activity of dacitic volcanoes. So this is the picture, yeah, from the lateral lava dome, Sowa Shinjen in Usu, yeah, volcano Hokkaido, Japan. And this is the surface deformations caused by the subsurface moving of the dacitic lava. And this is the picture of the explosive activity at Karamsky volcano. Yeah. And similar to the earthquake activity, actually in earthquake, there is something like the energy measurement that we call the magnitude in volcano environment. We 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 use volcanic explosivity index, VEI. Actually, the VEI is a relative measure of the explosiveness of the volcanic eruption. So it was published by Chris Newhall from United States of Geological Survey and Stephen Self, University of Hawaii in 1982. So actually the VI combined, yeah, actually grade ranging from 0 to 8, yeah, including total volume of explosive product, eruptive cloud haze, eruption type, and duration, and etc. And Newhall and Self proposed the range of VI for 5 main types of the volcanic eruption. So the first is the Hawaiian type with VI from 0 to 1, common for the basaltic volcanoes. And then second is Strombolian, VI 1 up to 2, actually common for the basaltic volcanoes. And the third is Vulcanian. So the VI actually from 2 up to 4, actually mainly at the andesitic and dacitic volcanoes. And the Philinian type with a PI 4 up to 8, actually common for dacitic and rhyolitic volcanoes. And the 5 is the ultraphilinian with the VI 5 to 8, actually common for the dacitic and rhyolitic volcanoes. Actually, we can see here the diagram from USGS actually here. This is VI from 0 to 8 with the example of the VI 0, Mount St. Helen in 2004. Mount St. Helen erupted in 1989. And we can see here Merapi volcano in Indonesia erupted in 2010. So, and also we can see here in Indonesia also Krakatau 1883 and Pinatubo in Philippines 1991 with the VI around here 6, yeah, and the Tambora 1815 with the VI around 7. And the highest is Yellowstone caldera 600,000 years ago. So this is the table show the general characteristic of the main type of the volcanic eruption. Yeah, this is the type of eruption: Hawaiian, Strombolian, Vulcanian, Philinian, Ultraphilinian, and this is the volume of ejected actually in cubic meters, and this is the column hay in kilometer, and this is the type of magma, and this is the eruptive style, and this is the volcanic features. Actually, we can see here each type of eruption has a characteristic different. And this table show the histories, the line eruption from the volcano of the world actually, and this is in the modern historical actually. We can see here there are 2 volcanoes from Indonesia, yeah, including Tambora volcano and Krakatau volcano. And this is the VI for Tambora is 7, for Krakatau is 6. And the year of eruption, Tambora occurred in 1812. Yeah, the number of fatalities 60,000. Yeah, and actually there are also another volcano, Ilofango, Vele, Nevado del Cruz, and Unzendake. Actually, this is the histories that lays eruption. And if we talk the seismological term, so first the rupturing along the fractures and fault, as well as the eruptive activity, produce the seismic waves, which could vibrate the Earth surface as earthquake. And then the site of the initial radiation of the seismic wave in the interior we call is earthquake focus or the hypocenter. If it just a projection to the surface is epicenter. So actually, everybody here well known about the seismic wave. Yeah, so this is just short brief review about the seismic wave. Actually, there are two main of the seismic wave, including body wave, body wave, and also surface wave. So body wave consists of the P wave and the S wave. Actually, this is the animation of the P wave propagation through the medium, and P wave has a characteristic as the faster wave, faster than S wave, and we call the primary wave. And the vertical motion is longitudinal for P wave, including compression and dilatation wave. So actually, this is the animation of the propagation of P wave through the medium. And then another of body wave is S wave. Yeah, S wave also we call the shear wave or secondary wave, and the particle motion is transversal wave. So the S wave commonly arrive after the P wave. So we can see here, this is the animation of the direct propagation and particle motion, yeah, passing through the medium. So for the S wave. And for the surface wave, the first is Rayleigh wave. So actually Rayleigh wave is something like retrograde elliptical, yeah, for the particle motion and also the propagation. And the Rayleigh wave actually arrive after the S wave, yeah, of course, yeah. And then another type of the surface wave is the love wave, yeah, something like the alternating transverse of the vertical motion and also the direction of propagation, something like this. We can see here, this is the type of the love wave. So actually, in seismological term, we use this wave to understand the medium, to understand the interior of the Earth, including the structure beneath or inside the volcanoes. So many application of the method using the seismic wave, yeah. Not actually, we can use the first phase rifle, we can use the wool fat of the waveform, and we can use amplitude, yeah, to understand the subsurface of the subsurface beneath the volcano actually. And this is the history of seismic monitoring of volcanic activity actually in the world, yeah, in general, yeah. So we extracted from the Zobin to 2012. Actually, earthquake were associated with volcanic eruption from the ancient time, so a long time ago. And then the Pliny the Younger delivered the first description of Vesuvius in AD 79. So he wrote about numerous earthquake related to this eruption at that time. And for many years, yeah, people consider volcanoes as the main origin of the earthquakes in general. And then the Vesuvius was the first volcano earthquake. Worst earthquake were mentioned in scientific literature. And 18 1947, the Vesuvius was the first volcano to have a volcano observatory and to be monitored using seismological equipment. And in 1862, the first seismic instrument to record the volcanic seismicity, seismogram were written on the telegraph tape. And in 1993, Bose Omori seismograph was installed at Mount Valley, Martinique, 1 year after great eruption of the 1902. Yeah, and 1912, the seismic observation at Kilauea, Hawaii, yeah, volcano had begun by Wood just after the foundation of the Hawaiian Volcano Observatory. And as a science, actually, volcanic seismology was born when the Japanese seismologist Pusakichi Omori had begun his investigation of seismic signals to the 1910 eruption of Usu and Asama volcanoes and the 1914 of Sakurajima volcano. And then in 1910, three component of seismic station with a magnification of multiply 100 and period pendulum of about 4 seconds actually was installed by the Omori at a distance of about 1 to 2 kilometers from the crater of Utsu volcano in Japan. So he demonstrated a good relation between the efference of the micro tremors and the explosion of the volcano. And in 1911 to 1913, so Omori showed many eruptions of Japanese volcanoes were preceded by the numerous earthquakes. And also he wrote that is the seismograph observation made at the vicinity of the center of the volcano activity would give people a warning of the approaching outburst. And in 1934, foundation of seismic observation at Asama Volcano Observatory on Honshu Island, Japan by Takeshi Minakami, and it was equipped by the continuously operated seismograph. And he proposed a classification of volcano earthquake into 4 types, which is the basis for study of volcanic earthquake up to the present day. So in 1946, Foundation of Seismic Observation at Kamchatka Volcano Observatory in Klyuchi, Kamchatka, Soviet Union at that time. And in 1950, high gain seismometer network at Hawaii Volcano Observatory has operated on Kilauea up to 1985 for about 50 seismic stations. And the seismic studies allow the construction of the earth crust model near the Hawaiian volcanoes. And in 1960, Eaton and Murata proposed the basic model of Kilauea with a magma reservoir at depth about 3 to 4 kilometers beneath the caldera. And 1987, actually, Klein et al. Showed the detailed history of volcano activity of Kilauea from the 1970. And in 1984, Klein showed the regularities of the inflation deflation cycle of magma reservoir and the inference of the characteristic related to seismic events combined with the ground deformation. Monitoring allowed the development of the short-term forecast of Hawaiian eruption. And actually, this basic investigation had become the foundation for the construction of volcano seismology as a science. During the last 30 years of the 20th century and the first 2 decades of the century, detailed and complex studies of some eruptions strongly increase our understanding of the seismovolcanic process. And it was shown that first, the source of the majority of E-type volcanotectonic earthquake is similar to the source of tectonic event. And the second, the record of explosive volcanic earthquake can be interpreted as landfalls excited by a nearly vertical single force that represent the counter force of the eruption. And the third, shallow earthquake in volcanic areas often have a mechanism with isotropic component, indicating a volume change of either explosive or implosive polarity. And many models have been proposed for explaining the nature of the volcanic tremor and long period volcanic earthquake. In addition, the development of methodology for volcanic eruption forecasting was developed. And the installing of the broadband digital equipment at volcanoes up to present day actually give a good perspective for better understanding the nature of the seismic signals originating with volcano activity. And this is the type of volcano earthquake and the terminology. Actually, active volcano are the source of a great variety of seismic signals. And then traditionally, volcanic earthquake have been classified based on seismogram, different into four different types. The first is high frequency or HF or volcanotectonic VT or A type. And the second is the low frequency LF or long period LV or B type. And the third is explosion quakes. And the fourth is volcanic tremor. And actually, this general classification scheme work well at the large number of volcanoes in the present day. And this is the example of the high frequency volcanotectonic or A type and its characteristic we can see here. And this is the example waveform in the top, and the bottom is spectrogram of the high frequency event. Yeah, this is from Kilauea volcano, Hawaii. And we can see here, actually, this is the X axis in the time, actually in second. And the Y axis is the amplitude. And we can see here, this is the spectrogram. The X axis actually in time, and the Y axis in frequency hertz, and the color indicate the amplitude of the wave. We can see here clear, this is the waveform of the high frequency content or VT event or A-type event. So this is the clear PNS wave onset. Yeah, we can see here, around here, we can see this is the V arrival, and maybe around here is S arrival. And then dominant frequency are from 5 hertz to 15 hertz. Actually, this is dominant from 5 to 15 hertz. Actually, maybe can be longer, can be shorter. We can see here clear for the frequency, high frequency event. And then high frequency are generated at source, but are not recorded, yeah, because of the instrumental limitation and high local attenuation. Yeah, this is actually, this is the challenge and something like constraint, yeah, for the recording of event in volcanic area. So due to the rock heterogeneity and the weak zone, and also something like field fluid for, and also something like partial melting that can be produce something like a high attenuation, absorb the energy of the wave. And actually magnitude are typically lower than 3, yeah. So we can see here, and also the characteristic of the high frequency event, yeah, at volcanoes. Earthquake typically occur in swarm, yeah, rather than main shock aftershock sequences. A swarm may be defined as a group of many earthquake cluster in space with no dominant shock. In practical term, the difference in magnitude between the largest and the second largest event of SWAM is commonly 0.5 magnitude unit or less, as opposed to 1.0 magnitude unit or more for most many shock aftershock sequences. And this is the example of the hybrid event and its characteristic. So we can see here, this is the example of the waveform, and this is the spectrogram. So actually, if we see here, the characteristic of the hybrid event, including share attribute of both high frequency and low frequency event. You can see here, this is relatively high frequency here, and this part relatively low frequency. So this is the mix, yeah, the mixing between the high frequency and the low frequency. So we can see here, this is the relatively high frequency, and here is the low frequency. And the display show high frequency onset of an high frequency event, but the later part of the signal, something here, this is the coda, is similar to low frequency event, yeah, around here. And the hybrid events may represent a mixture of the processes such as an earthquake occurring adjacent to a fluid field cavity and setting it into oscillation. So other suggest is hybrid are shallower than low frequency event, and those preserve most of the high frequency energy that is attenuated for a different event. And this is for the hybrid Earth event. And this is the example for the low frequency, long period or B-type event. And this is the example of the waveform, and this is the example of the spectrogram. Yeah, we can see here, this is low frequency content clearly. Yeah, we can see here, this is the low frequency event type, and the characteristic of the low frequency event, including first the emergent P waves, yeah, emergent P wave, and the lack distinct S wave, and also this is the dominant frequencies between 1 and 5 hertz, with 2 up to 3 hertz being the most common actually. And then the most low frequency event are thought to be caused by fluid pressurization processes, such as bubble formation and collapse, and also by shear failure of rock, or nonlinear flow processes that occur at very shallow depth, for which attenuation and
Sorry, perhaps something happened with the internet connection. Be waiting for a while for internet connection of Professor Andri Dian Nugraha.
period actually has similar and lower frequency. We can see here distinct S wave, and also we can see here dominant frequency between 1 to 5 hertz, with 2 up to 3 hertz being the most common, and the most low frequency even here, or diff long period here, are to be caused by fluid pressurization process, similar to the low frequency event actually in the previous one. So, and this is the volcanic tremor. Yeah, we can see here, this is the example with waveform of the volcanic tremor. And this is the spectrogram of the volcanic tremor. So the volcanic tremor actually has characteristic, yeah, as follow. Continuous signal with the duration of minutes, today, or longer. So it can be shorter, it can be longer. So, and then the dominant frequencies of the tremor are about 1 up to 5 hertz. Yeah, where the 2 up to 3 hertz is the most common and similar to the low frequency event. Many investigators have concluded that tremor is a series of the low frequency event occurring at interval of a few seconds. And this is the example of the very long period. So actually, so many types of the volcanic earthquake signal, right? So this is the example of the very long period. Yeah, something like this actually. This is the waveform of the very long period, and this is the spectrogram of the very long period event. So the characteristic is the something like this. Broadband seismometer have ability to detect ground motion over a wider frequency band, particularly at the low frequency end, down to frequency equal to 0.016 hertz or period of the 60 second and lower. Now, not surprisingly, a new class of event called very long period event has been observed at some volcanoes using broadband seismometer. So actually, observation to date show even with period of 3 up to 50 seconds, originating from a shallow depth of about 1.5 kilometer or less, yeah, under several active volcanoes, including Kilauea, Hawaii, Stromboli, Aso volcano in Japan, Sakurajima volcano in Japan, Fuego, Augustine in Alaska, and Stasuma Iwo Jima. And some current models suggest very low period, maybe produced as magma moves through a flavor path. Yeah. Additionally, theoretically, calculations show a very long period possible for a crack or tube filled with fluid to produce the long period. And this is the example of the explosion earthquake, something like this. And this is the waveform. And this is the spectrogram. And for the explosion event, accompany explosive eruption. And many are characterized by the presence of an air shock based on seismogram. And there is a partitioning of energy at the source, including part of the energy travels through the ground as seismic wave, and part travel through the air as acoustic of airwaves. The airwave then couple back into the ground and is detected by the seismometer. And this is an example for the rockfall event. Yeah, this is the waveform, and this is the spectrogram. We can see here the rockfall event actually are a special type of landslide, yeah, in which one or a few pieces of bedrock become detached and free fall. They are especially common at the edge of volcanic domes and at volcanoes with very steep slope or cliffs. In display here show the seismogram of strong local signal lasting more than 1 minute actually. And this is the axis for the second actually. This is more than 60 seconds or more than 1 minute actually. So in summer of the 1995, worker at the Mount Spur, Alaska, observed rock more than 1 meter in diameter, falling several hundred meters and impacting on the crater floor. So we can see here, this is the recording of the rock fall at the time. And this is example of the seismogram of the several type of the volcano event in Sinabung volcano in Indonesia. Actually, this is Sinabung volcano as indicated by red triangles and the black triangles, the peak for the active volcanoes in this area. And actually, Sinabung volcano erupted on 2010 at the time, and still show the eruption activity up to present. Yeah, and we can see here this is the example of the seismogram from the 2013 activities at the time. So here, SIG dominant seismic signal type recorded at Sinabung volcano. Yeah, for here, recorded by station SKN. Actually, this is from Pak Gunawan et al. He come from the Volcanological Survey of Indonesia that we call PPMBG. So, and we can see here, this is the waveform, and this is the spectrogram. Axis for the time in second, and the y-axis for the frequency in hertz actually, and the color indicated for the amplitude. So we can see here, this is the example of the distal VT, yeah, distal VT or volcanic tectonic event, distal equivalent or similar to SWAM event actually. And we can see here clear for V arrival and clear for S arrival. And we can see here the frequency content of this event, yeah. And this is the shallow VT, yeah, the example of the seismogram for the shallow volcanic tectonic event or shallow VT, yeah, we can see here. We can see clearly P arrival, and maybe difficult to see for the S wave, yeah, because the shallow event we can get the very narrow of the different time of S and V arrival time. So actually, if we zoom in the seismogram, maybe we can distinguish this is P, this is S arrival times. And this is the hybrid event. Yeah, this is mixing high frequency in the beginning of the coda wave, and this is the low frequency content in the late of the coda wave. And this is the example of the low frequency. We can see here. This is we can see actually fairly clearly by eyes. Yeah, if we compare to the high frequency, even from the distal VT, for example, we can see here the low frequency something like this for the waveform. And from the spectrogram also, it's the less than 5 hertz for the dominant frequency, actually for the low frequency. And another type is emission. Yeah, we can see here something like this, and this is the tremor. We can see here, this is something like this. And this is the example seismogram from the Sinabung volcano in Indonesia. And this is the selected volcano seismology terminology, and the table show actually we can see here there is something like high frequency in this article actually in Magnat and Roman 2015 referred to this article actually. This is they call the high frequency or HF, and the study from the Minakami in 1960. He called A type, and from later 1979 he called the tectonic or volcanic tectonic, and the AVO here, Alaska Volcano Observatory, they use terminology of the volcanotectonic or VT, and other names is short period earthquakes. And from McNatt and Roman, 2015, for the low frequency event, Minakami called the B type, and also later in volcanic, called volcanic or medium frequency, and AVO long period hybrid, and other name long coda event, tornillo and mixed frequency. Yeah, tornillo, maybe we can I didn't show the tornillo waveform, for example. Actually, something like screw, yeah, something like if we something like, sorry, the tornillo is like something like sorry, maybe something like this tornillo. If we, this is the x-axis, maybe something like this. Yeah, this is the tornillo. Sorry, this is not good for. This is something like this. So this is the tornillo event. And then we can see here also hybrid, later called the medium frequency, and AVO called the hybrid. And other name is mixed frequency, and also explosion quake, and also the volcanic tremor. And this is the selected volcano seismology terminology. And actually, what is the objective? What is the goal of the volcano seismology? The goal of the volcano seismology actually include the first, monitoring the present state of a volcano, and the second is forecasting eruption and other change in volcanoes activity when the end of an eruption, for example, and estimating the size of eruption in progress, locating magma chamber, and understanding the physical processes that are occurring within the magmatic system. And actually, that's all. And the general features of the earthquake at volcanoes. Actually, this is the selected. First, commonly we talk the seismicity rate and the background. Actually, the volcanoes nearly always have a non-zero background level of seismicity caused by heat zone underneath and movement of groundwater and volatile or magma, glacier if present, and landslide, rock falls, a reaction to stresses from regional tectonic and tides, other forcing function. And those baseline of measurement of at least at few years duration is necessary to characterize and understanding the background seismicity. And many successful eruption forecasts have been made because of an increase in seismicity above previously recorded background level. And another general feature is seismicity associated with large versus small eruption. In general, a large eruption, yeah, are relatively easier to forecast than smaller ones. And the amount of magma involved is large, and frequently earthquakes tend to be numerous as well as distributed over a large volume. Other precursors, such as deformation and steaming, are usually observed in conjunction with earthquake swarm. For example, Pinatubo, Philippines, 1991, Spur, Alaska, 1992, Augustine, Alaska, 2006, Kasatochi, Alaska, 2008, Red Dove, Alaska, 2009, Eza, Jalazokul, Iceland, 2010, and Merapi, Indonesia, 2010. Small eruption and many phreatic or water-driven eruption, in contrast, involve much smaller of magma and have subtle precursor or sometimes no observable precursor. They are therefore generally harder to forecast. Recent examples include Galeras, Colombia in January-June 1993, Arenal, Costa Rica, August 1993, Wyatt Island, New Zealand, February 1992, and Ontake, Japan, September 2014. And the other general features of the earthquake at volcanoes is location of volcanic earthquake. Actually, this is one of the important to show, to know where is the location of the VT event beneath the volcano area. So generally, volcanic earthquake occur beneath the point of eruption. Yeah. For example, in proximal cluster, this help reduce the monitoring problem to that of estimating the time of eruption, since the place is considered known. For example, seismicity preceding the 2004 eruption of Mount Helm, Washington, occurred in a small shallow volume approximately 1 kilometer below the eruptive band. However, several cases have occurred in which the location of initial precursory earthquake swarm did not coincide with the eruptive fan. For example, distal cluster, for instance, the initial earthquake swarm prior to the dacitic eruption of Mount Pinatubo, Philippines in 1991 occur about 5 kilometers northwest of the volcano. Yeah, 12 days before the climatic eruption, activity of this swamp declined and vigorous shallower swamp began beneath the eventual eruption site. And the other general feature is large regional earthquake near volcanoes. Yeah, this is the large regional earthquake are believed to occasionally trigger eruption. Proposed example include the eruption of Hui Chaili 48 hours after the magnitude 9.5 earthquake of 1960 and 1999 eruption of Cerro Negro, Nicaragua, 3 days after a series of nearby of magnitude 6.5 event. However, such example of static triggering are difficult to prove, yeah, conclusively, and the exact mechanism of erupting triggering is also not well understood and still discussion actually. And proposed mechanism include local stress change near the volcano induced by the nearby large event, analog to squeezing a tube of toothpaste, and several mechanisms involving the displacement of or growth of bubbles by passing seismic wave. Most well documented example of dynamic triggering involve trigger episode of non-eruptive volcanic unrest. For example, the only documented example of volcanic unrest triggered by 2004 magnitude 9.1 Sumatra Andaman earthquake was at Wrangell Volcano, Alaska, around 11,000 kilometers away, which experienced a series of the 14th volcanic event during the passage of the surface wave through the volcano. Immediately after the 2011 magnitude 9 Tohoku earthquake in Japan, a swarm of over 1,600 events was recorded at the question Hakone volcano, 450 kilometers away, that included a multiple failed earthquake. A proposed example of static triggering earthquake unrest, for example, June 1992, magnitude 7.3 event in Landers, California, remotely trigger event swarm at 17 volcanic areas in the western United States at distance of about 165 to 1,250 kilometers. Although no eruption occurs, this one demonstrated that a small transient stress change can trigger significant change in seismicity in volcanic areas. And another feature is caldera earthquakes. Actually, large earthquakes often occur at large structures such as caldera. For example, magnitude 6 event have occurred at or near the caldera in Long Valley, California, Yellowstone, Wyoming, Montana, and Idaho, and also Japan, magnitude of 5.1 event have occurred at Rabaul caldera, Papua New Guinea in 1982 and 1984, while small eruptions have occurred frequently at the central vent of Aso. No eruption have occurred at Long Valley or Yellowstone. Rabaul caldera in Papua New Guinea finally erupted on September 1994, following 13 years of caldera-wide seismicity and 27 hours of intense local seismicity. Actually, it is normal for large caldera to show frequent signs of unrest, the vast majority of which are not a precursor to eruption. This adds to the uncertainty in dealing with earthquake swarm at calderas. False alarm are more likely, but large eruptions are also possible. And the other general feature of the event at volcanoes is how to delineate the magma chamber and or to see the magmatic plumbing system actually using the seismicity parameter, yeah, using the seismic wave, for example. And this is the tomographic image, yeah, for the P wave structure beneath the Rabaul caldera in Papua New Guinea, actually. And we can see here, this is the green color for the low PV and the red color for the high PV value, actually in absolute value in kilometer per second. And the lower panel is the same, actually the same tomogram, but are plotted in the velocity contrast in actually in percent, yeah. Maybe deviation to the initial reference model, for example. And this is high anomaly or high percent in VS, in PP, sorry, indicated by the blue color and the red color for the negative anomaly. We can see here, and this is the caldera of the Rabaul, yeah, and we can see here, this is the low velocity of PP structure. And magma is thought to be stored in the sometime of magma chamber or reservoir underground. And seismology is useful for determining the size, the shape, and the location of the such chamber. And magma chambers at stratovolcanoes appear to be generally equal in shape and on the order of the 1 up to 20 kilometer cubic in volume. Those at calderas are larger, and the majority of depth up to the top are at about 5 to 20 kilometer or deeper based on the tomography, as web screening and the post-eruption seismicity. And this is the example from tomography of Merapi volcano Indonesia. Actually, Professor Sriwantoro already mentioned in the beginning of our session. Yeah. Now, actually, this is the collaboration between the French researcher from France and from Indonesia. And at the time, actually, in the 2013 up to 2015, yeah, we installed about 46 seismograph station around the Merapi volcano and in central Java, Indonesia. Merapi volcano actually is the one of the most active volcano in the world. Yeah, actually, at the time, Pak Zulpak Rija involved and install some seismograph, yeah, Pak Zulpak Rija, in Merapi.
Yes, 2013 to 2014.
Yeah, when we were young. No, I still young at that time. So yeah, 46 station at that time, and then for the tomographic invasion, the temporary station and the BMKG station, we combine, yeah, to determine the PP structure, VS structure, and ratio PP structure in order to see the magmatic plumbing system, yeah, beneath Merapi at the time. And this is for the structure of ratio PP over VS, and this is for the structure of PP structure, yeah. Red and blue color here indicate for the low and high value for PV and also for PP and ratio PP per VS here. And this is the tomographic of Sinabung volcano in Indonesia. Yeah, at the time, actually this is collaboration ITB and also Volcanological Survey of Indonesia, PPMBG here. We try at the time to determine the PPVS and ratio PPPS structure using the data in Sinabung volcano from November to December 2013. Yeah, at that time, we used around 4,846 volcanotectonic event for the tomographic inversion, as we can see here. And this is the epicenter distribution around the Sinabung volcano. And we acknowledge at the time we have limitation of the number of station. For example, the reverse blue triangle here indicate for the seismograph station at the time. 1, 2, 3, 4, 5, 6 station, only 6 station. We try to optimize the tomographic inversion at the time. And this is the hypocenter distribution beneath the Sinabung volcano in the period of November to December 2013. Here also we collaborate with the PDAF, yeah, USGS at the time, Wendy Kausland here. And this is the selected result of the tomographic impression in Sinabung. This is for the structure of the ratio PP per VS. Blue and red indicate for high and low PPPS ratio value respectively. So the both cycle black field cycle is the hypocenter beneath the Sinabung volcano at the time. And we can see here, this is the structure of the PP upper VS. We can see clearly here, some region, some zone here show the high PP upper VS ratio. Of course, we have to compare with the PP and VS value if we want to interpret it in the more detail and more precise. And then this is the general feature of the source versus path and side effect. Yeah, actually, if we discuss about the waveform in a volcanic region, of course, we have to consider the side effect and the path effect related to the attenuation. Yeah, and we can see here, this is a long-standing issue on volcano seismology is the relative contribution of the source and propagation, including path and side effect on the resulting seismogram. There are, for example, there are two stations. This is MMB station located here, and this is MMF station locating here. And the cross is the location of epicenter, and the location actually not so many different in epicenter distance for the MMB and MF station. And station MMB is located on an old dome and is essentially a bedrock site. So this is the hard rock actually. MMB is located in the hard rock for the sensor. And the earthquake appear to be ordinary high frequency event. And this is the waveform of the MMB station. So MMB station is located in the concrete rock or hard rock. We can see here the waveform is dominantly high frequency content. And then for the station MMF around here, the information is the station is located in a sediment site. So the event look like a single low frequency event with the extended caudal. And this is the MMF that is located in the sediment, sub-sediment. So we can see here, clearly here, this example clearly demonstrates that the high impact of a path and side effects on the resulting waveform. And then we go to the Indonesian region. So actually, this is the tectonic of Indonesia region. So the Indonesian region is affected by four major plates, four major plates in the world. So in the southern part, there is Indian plate, Australian plate, and in the eastern part, there is Pacific plate and the Micro Caroline plate. And the northern part, there is Philippine Sea plate and the Eurasian plate is locating here. So of course, this is the one of the most active tectonic and complex geology in the world. So the implication is many seismicity in Indonesia, as shown here from the BMKG, Badan Meteorologi, Klimatologi, Geofisika Indonesia. This is from 2009, 2015. We can see here from the Sumatra, Java, Nusa Tenggara. This is Banda Aceh, Molucca, and this is Sulawesi, and this is the Papua. We can see here many source of the event. Due to the subduction or due to the active fault or inland active fault, we have well-known inland active fault, for example, Sumatra fault, and then Palu-Koro fault, and also something like Sorong fault here. And another implication here is we have so many active volcanoes in Indonesia. Sorry, the sentence here in Indonesia, but I will try to translate to English. This is from the Volcanological Survey of Indonesia. We can access here. Actually, I just access yesterday. We can see here. Yeah, we have 127 active volcanoes in Indonesia, and Volcanological Survey of Indonesia divide into 3 types, including A type, B type, and C type. Yeah, this is from Sumatra Island, Java Island, sorry, Bali Island, Nusa Tenggara, and this is the Banda Sea, and this is the North Molucca here, Halmahera, and this is the northern of the Sulawesi here. So this is around the we have 7,000 kilometer of the volcanic front line. Yeah, lines from the Sumatra, Java, Bali, Nusa Tenggara, Banda, Halmahera, and north of Sulawesi. And around the active volcanoes in Indonesia, around 4.5 million people are living around the active volcano. So actually, this is the implication of the active and geological complex in Indonesia for the active volcano. And in Indonesia, we have something like warning, yeah, PSI or PPMBG divide into 4 levels actually, and this is the lowest level, and the number 4 here is the highest level, yeah, for the level warning of the volcano activity. And this is the last session actually. I would like to inform our activities at ITB. Actually, we have some activities about the volcano study. Yeah, this is one of our activities at ITB, seismological monitoring using then seismograph network around the Mount Agung and Batu Caldera in Bali, Indonesia, supported by USA through the FEAR and also collaboration with the Volcanological Survey of Indonesia, VSI, of PPMBG, and NSF here. And this is our team actually, yeah, for the seismological group. And then the objective of the study is to determine the volcanotectonic or VT location around the Mount Agung and Batu Caldera in Bali, Indonesia, and to determine seismic structure, yeah, PPVS, ratio PPVS, and attenuation structure, 1 per Q, 1 per QV, and 1 per QS, derived from the travel time tomography and also the ambient noise tomography, and also to determine the magmatic plumbing system model actually, yeah. And this is the seismicity during the 2017 crisis in Agung volcano. Actually, this is the Agung volcano as indicated by black triangle, and this is the Batur caldera, and there is also Mount Batur here, and the color of the reverse triangle stand for the seismograph station, yeah, during the 2017 crisis at the time, operated by PSI or PPMBG station, PPMBG in Indonesia. And this is from the David Sahara publication, yeah, recent publication in Frontier in the Frontier in Earth Sciences 2021. And this is the seismicity during 2017, yeah, from October 2017 and November 2017. And this is the phreatomagmatic eruption, and this is the magmatic eruption in November 2017. Yeah, actually, this is the data from PPMBG, and we can see here. This is the example of the waveform, yeah, at the time, and this is the location of the event as indicated by yellow star, and the black and the reverse triangle is the station of the seismograph around the Agung and Batur. And we can see clear here, this is for V phase arrival, and this is for S arrival, and this is the Wadati diagram to validate our picking of P and S arrival time. Actually, we conducted P and arrival time peak phase manually by eye. So we see one by one the event, yeah, and then we try to see the result and validation using the Wadati diagram here. And this is the seismicity during 2017. All even here we pick P and S arrival manually by eye. So actually there are many events at that time. And this is Agung volcano, and this is Batur volcano, and the 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 purple cycle here indicate for the event that occur in October 2017 during the seismic crisis, and the blue cycle here indicate for the event that occurred after the crisis in November 2017. Actually, it seemed to be different in the distribution of the epicenter. So during the crisis, the epicenter is location here, and after the crisis, the epicenter is to be something like the diffuse, sparse, yeah, something like that. And this is the vertical cross section through the B section, and this is through the C section. And B section, this is from the actually northwest to the southeast. This is northwest, this is the southeast, and for the C, this is southwest, and this is the northeast actually. This is Agung, and this is Batur. Yeah, something like this. This is the this is during the crisis as indicated by purple cycle, and this is the after the crisis here. And then we use this data of the PNS arrival time to determine the tomograph to the PPVS and ratio PPPS structure using tomographic inversion. This is from Ardianto, published in Frontier in Earth Science this year. Actually, we use the seismograph station only from the PPMBG, from the PSI station here during the crisis. And we can see here, and this is the parameterization model in tomographic inversion as in a grid node as indicated by black pluses here. We can see here, and we try to optimize the data and to see the result of the tomographic inversion. And this is the vertical cross-section passing through the Batur and Agung volcano. And this is the schematic diagram from derived from the ratio PPVS ratio structure. Red is high PPVS structure, and blue is low PPVS structure. We can see here, and then we try to interpret it. Maybe this is the magma, deep magma storage, and maybe this is the dike intrusion, and this is maybe the shallow reservoir beneath the Agung volcano. And then 1 year after the Agung crisis in 2017, we develop, we deploy the dense temporary seismograph network in November 2018, actually, up to December 2018 at that time. So before the COVID-19 pandemic. So, and this is the location of the Agung volcano, and this is the caldera Batur, and this is the location of the temporary seismograph that we deploy at the time. So we have been successfully installed about 25 stations from November 2018 up to September 2019 at that time. And this is our teams. yeah, coordination with the PPMBG or CPGHM in Bali, Bali Agung Volcanological Observatory at the time. Thank you for PPMBG. And the photos were taken in November 2018. Yeah, this is before pandemic. You can see here our team, and also we coordinate with the local authority in Bali around the Agung volcano, around the Batur volcano, with the government, local government, with the military uh, in the fields actually. So this is the situation of the temporary seismograph installation at the time. So we can see here, and this is the sensor of the seismometer and connected to the digitizer or data logger. And here we use the solar panel to charge off the battery for the recording of the event. And, and this is the final setup at the time for the seismograph temporary installation. And yeah, our activities is also reported by media, local online news media at the time. Yeah, in Bali Pos and the Radar Bali. Sorry, this is in Indonesian, in Bahasa. And then, and this is the example of the regional event that recorded by our temporary seismograph station at that time. This is for event occur on February 20, 2019, local time 16 minute 49 10, and this is for regional event. Yeah, we can see here. This is for the P arrival time. This is from the 3-component seismogram for each station, and this is for S arrival time. Yeah, we can see here, and this is the difference of S and P time, or about 17.7 seconds, and the lowest is about 14 seconds. It means the event is not located around Agung and Batur volcano. Yeah, so outside Bali Island, maybe in the certain part from the subduction zone, or maybe from the northern part, yeah, from the Banda Sea, or maybe around that. And this is the example of the local event recorded by temporary seismograph station at the time. We can see here the event occurred on February 24, 2019, local time for 4 and 51 for 18 at the time. And this is the shortest of the time difference of S and P is 1.5, 1.4 second. And this is the longest is the S minus P time 4.6 second. So it means the location of the epicenter is close to the Mount Agung or Batur Caldera at the time. So, and this is the zoom in example of the volcanotectonic event in occur on March 15, 2019. And this is yeah, very narrow. Yeah, the difference between S and P arrival around 2 seconds. And during our recording of temporary seismograph, we observe also the eruption on March 15, 2009. We can see here FEAR and LEAF seismograph PPMBG. Yeah, we can see here. This is the situation during the eruption on March 15. And then we check the data at our temporary seismograph station, and we observe around here. And we can actually at the time we record the eruption event. And then another eruption on April 11, 2019, and this is reported by PPMBG. Yeah, and then we check in our seismogram something like this. Yeah, this is the location, this is the event, the waveform for the eruption event on April 11, 2019. And this is the result, and this is the actually this is the preliminary result at that time. Actually already done. Yeah, and this is thanks to Dian, Yayan, Billy, and the teams who picks manually PNS arrival time And at that time, up to May 2019, we got to 130 events, including 3,500 PPS and 3,000 species, yeah, and the hypocenter determination using non-linear location from Lomek et al. And one seismic velocity from regional local from Kuyakov et al. 2007. And the reverse blue triangle indicate seismograph for the temporary station, and the white cycle indicate for the epicenter distribution here. And this is the some vertical cross section actually from December 2018 up to May 2019. And actually, sorry, the result of this current time period is ongoing in our manuscript. Yeah, first for the seismicity, second for the velocity tomography, and then for the attenuation tomography. And this is the result from the Pak Zulfakrija, yeah, using the temporary seismograph station from the ambient noise tomography, yeah, published in 2021 or 2020, Pak Zul. I forgot. Maybe last year.
2020, Pak Andri.
Okay, last year, yeah. So we can see here. And this is the result of the ambient noise tomography in the horizontal section at depth of 1 kilometer. This is for the VS structure or surface or shear wave velocity structure, yeah, at depth of 1 kilometer. And this is the vertical section from south to the north, west to the east, yeah, something like this. And this is finally, we have video movie from our activities during the download, during the deployment, and so on in Bali. Please enjoy. Okay, can you hear?
Perfectly.
Okay, thank you. Let's enjoy. This is our activity in Bali at that time. This is in 2019, before pandemic, yeah. This is the sensor. Discussion with the local authority. There is one of station was broken at the time. It's difficult access to reach the site of the seismograph location. This is Agung Volcano Observatory in Bali, operated by PPMBG. small at that time. So the team must go to the site by walking around 2 kilometers. Situation in the field. This is Mr. Yopi, our team. Base camp in Kintamani, clean up the tools. Okay, okay, that's all that I had. Actually, thank you very much. Terima kasih, hatur nuhun. So thank you very much, Pak Zul and all.